Good day, everyone. Today we are dividing into the fascinating world of two-degree freedom systems, specifically focusing on how to determine their natural frequencies. This is a crucial concept in understanding and controlling vibrations in various engineering applications. This lecture is part of our Unit 2, that is, studying two-degree freedom systems. And we will be analyzing the system's behavior using displacements in terms of X. My name is Dr. C. Sendamarikanan and I am Associate Professor in the Department of Mechanical Engineering at SPC. Before we delve deeper, let's take a moment to see what we will be covering in this lecture. First, we will start with a brief introduction to the concepts of vibrations with respect to two-degree freedom systems, setting the stage for more in-depth discussions. Next, we will explore the equation of motions specifically for two-degree freedom systems. This involves understanding how the damping and stiffness forces affecting the behavior of two-degree freedom systems. Finally, we will analyze the free vibration of undamped systems and we will calculate natural frequency for the systems with and without damping. Let's begin by understanding the fundamentals of two-degree of freedom systems. These systems are essential in various engineering fields from mechanical vibrations to structural dynamics. Here we can see the two-degree of freedom systems. As the definition states, two-degree of freedom systems are characterized by the need for two independent coordinates to fulfill to describe their motions. Think of it as having two distinct ways in which the system can move. Here, this figure showing the building mass on springs. To illustrate this, consider a simplified model which is represented in the form of building. This is the mass of the building supported by spring on either side. Building can move both vertically up and down and rotate about its base. Here it is given, it is rotation. This is going to be the displacement. These two type of motions constitute the two-degree of freedom in the systems. While real-world systems can be much more complex, this simplified model allows us to grasp core principles of two-degree of freedom systems without overwhelming complexity. Now, let's clearly distinguish between one-degree of freedom systems and two-degree of freedom systems. Understanding this difference is crucial for accurately analyzing vibration behavior. We will look at some visual examples. Firstly, let's consider a simple one-degree of freedom system. Here we are having a mass m connected to a spring with stiffness k. This system can only move in one direction represented by the displacement x. Therefore, only one coordinate x is needed to describe its motion, hence it is a one-degree of freedom system. Next, we will move on to the torsional pendulum. We have a disk that can only rotate about its vertical axis. The motion is described by the angle theta. Again, only one coordinate theta is needed, making it a one-degree of freedom system. Now let's move to a two-degree of freedom systems. In this example, we have two masses m1, m2 connected by springs. The position of each mass is defined by x1, x2 respectively. Both x1 and x2 are independent coordinates. We need to specify both x1 and x2 to fully describe the motion of the system, making it a two-degree of freedom system. Similarly, In this torsional system, we have two disks with mass moment of inertia J1 and J2. Their rotational motions are described by angles theta 1 and theta 2. Both theta 1 and theta 2 are independent, making it a 2 degree of freedom torsional systems. We need both angles to define complete motion of the system. So, to summarize, 1 degree of freedom systems require only one coordinate to describe their motion, while 2 degree of freedom systems require two independent directional coordinates. This fundamental difference is key to analyze and understand their vibration characteristics. Let's formulate how we determine the number of degree of freedom in a system. This is a crucial step in analyzing the system's dynamic behavior. The general rule for the computation of the number of degrees of freedom can be stated as follows. It is number of degree of freedom of a system is equal to number of masses in the system multiplied by the number of possible types of motion each mass can have. So this is the formula to determine the number of degree of freedom of any given system. Let's break this down further with an example. In this figure, we have an instrument represented by mass M surrounded by packaging or cushioning material. Think of this as a delicate instrument being protected inside a case. Packaging material can act like a springs, allowing the instrument to move in all three translational directions along the x, y and z axis. Therefore, each mass has three possible types of motion. Since there is only one mass in this system, number of degree of freedom is one mass times three possible motions, giving us 3 degree of freedom systems. But as far as this figure concerned, we are considering this as to be in two-dimensional plane. Hence, we can't think about this instrument with perpendicular to this PPT. Hence, it is going to be considered only in x and y axis. So, let me see that this instrument is connected only upon the springs of y axis up and down and x axis up and down. So, this is represented in this way that the mass can move in any one direction in x axis and y axis. Understanding this, we can simplify further that earlier we thought that this is a three-dimensional object. Now we are thinking it is a two-dimensional object having a thickness of minimum thickness. It is not a huge thickness. So we have modeled that into a mass having two springs. One spring is moving in the x-axis, another spring is moving in the y-axis. So now the mass can able to make how many number of motions? It can able to make only two possible motions, that is one on x-axis, another on y-axis. So it is going to be clearly seen that from this diagram that the number of degree of freedom for this given system is 2. As is evident from the systems shown earlier, the configuration of a system can be specified by a set of independent coordinates termed as generalized coordinates, such as length, angle, or some other physical parameters to determine what is the degree of freedom for the given systems. Now, we move on further. The equation of motion for the 2 degree of freedom system. Understanding these equations is essential for predicting and controlling the system's behavior. Maybe it may be free vibration, otherwise a forced vibration. Now we are considering the viscously damped system. Here we are adding the dampers, meaning it includes damping forces that resist motion, much like a shock absorber in a vehicle. This is a more realistic model than an undamped system, as damping is present in most real-world applications. In this figure, we see 2 degree of freedom systems. We have two masses M1, M2 connected by springs with stiffness K1, K2, K3. Each mass is also subjected to external forces F1 of T, F2 of T and dampers C1, C2, C3. Figure B shows the free body diagram of these masses. We have included all the forces acting on each mass, including spring force, damping force, external force, that is F. Notice how the spring forces depend on the relative displacements between the masses. For example, the force K2 depends on the difference between x2 minus x1, is it not? Because it is dependent upon both the x1 displacement as well as x2 displacement. We have the spring force K1 x1, damping force C1 x1 and external force C1. Similarly, the spring force K2 x2 minus x1, damping force C2 x2 minus x1. Similarly, in the other hand, we are also having K3 x2, C3 x2, that is a damping force, and F2 is going to be the force acting on the mass 2. These free body diagrams are crucial for deriving the equation of motion. By applying Newton's second law, we can sum the forces acting on each mass and set them equal to the mass times the acceleration. This will give us two coupled differential equations which describe the motion of this system. Now let's move on to deriving this equation of motions from the next slide. Continuing from our previous discussion, we will now derive the equation of motions for our viscously damped 2 degree of freedom systems. As we mentioned, these equations describe the system's dynamic behavior under the influence of external forces. Application of Newton's second law of motion to each of the masses give this equation of motion. That is, we recall what is Newton's second law, which states that sum of the forces acting on a mass is equal to mass times its acceleration. By doing this for each mass, we obtain two coupled differential equations. First, let me look this equation. This represents motion of mass m1. We have m1 times acceleration, that is x1 double dot. Then we have terms involving damping forces, spring forces and external force. Notice how the damping force and spring forces depends on both x1 as well as x2, reflecting the coupling between the two masses. Similarly, the second equation describes motion of mass m2. It includes mass times the acceleration, damping terms, spring terms. Also here we can able to see coupling terms x1 and x2 in the damping and spring force terms. These equations can be elegantly expressed in matrix form, which further simplifies our analysis and allows us to use linear algebra techniques. Here, M is the mass of the matrix, C is the damping matrix, K is the stiffness matrix. These matrices capture the system's mass, damping and stiffness properties respectively. The vector x double dot represents acceleration vector, x dot represents velocity vector, x represents displacement vector, and f of t is the external force vector. The mass matrix is a diagonal matrix with m1, m2 on the diagonal, indicating that the masses are uncoupled in terms of inertia. Damping matrix C and stiffness matrix have off-diagonal terms representing coupling between the masses due to damping and spring forces. These matrices are crucial for solving the equations of motion and understanding the system's dynamic behavior. By using matrix notation, we can easily manipulate and solve these equations, making our analysis more efficient. Now, let's move on to Let's take a closer look at the mass, damping and stiffener matrices we introduced earlier. These matrices are fundamental to understanding the dynamic behavior of our 2 degree of freedom systems. We already discussed mass is having a diagonal matrix which is uncoupled in terms of inertia. Damping and stiffness matrix both are coupled with respect to the term, that is, it represents the it is connecting the mass m1 as well as mass m2, that is the coupling between the masses due to the damping forces, similarly coupling between the masses due to the stiffness forces. And the displacement and force vectors are given respectively. It can be seen that mass matrix can be written as M, C and K are symmetric. You can see that it is symmetric in nature, where the superscript T denotes the transpose of the matrix. In this slide, we are making a very crucial step in understanding the natural behavior of 2 degree of freedom systems. Free vibration occurs when the system is allowed to oscillate without any external forces. So here we can see that if we consider it is going to be free vibration, forces should be taken as 0. That is, the general solution of equation of motion for forced vibration involves 4 constants of integrations, 2 for each constant. To simplify our analysis, we first consider free vibration solution, which will help us to understand system inherent dynamic capacities. So let me put f1 of t, 2 of t equal to 0, and damping is disregarded. That means C1, C2, C3 is 0. To analyze free vibration, we set the external forces are 0. This simplifies our equation of motion and allows us to focus on the system natural oscillatory behavior. Hence, the system equation of motions are reduced to these 2 simpler equations. These equations represent free vibration of our undamped 2 degree of freedom systems. Let we assume that is possible to have harmonic motion for the masses m1 and m2 at the same frequency omega and the same phase angle pi. Let we assume the solutions are x1 of t, x1 cos omega t plus pi, x2 of t, x2 cos omega t plus pi. So here the phi is the phase angle, omega is the frequency at which the system is going to be oscillate. This assumption is based on an idea that this free vibration must oscillate together in a coordinate manner. Building on our previous discussion, we will now substitute the assumed solutions for x1 of t, x2 of t into the equations of motions we derived for the undamped system. This will lead us to the frequency equation, which is crucial for determining the natural frequencies of the system. We assume that x1 of t equals x1 cos omega t plus pi, x2 of t equals x2 cos omega t plus pi. We will now substitute this equation in the 4 and 5, which we seen in the earlier slide, which represents the free vibration of our undamped system. After substituting and simplifying, we can arrive these equations. Notice that both equation contains the term cos omega t plus pi. This equation must be true for all values of time t. The terms within the square brackets must be equal to 0. This is because cos omega t plus pi can take various value between -1 and t, and for the equation to be always 0, then the other term, this is within the square bracket, must be 0. Therefore, we get these 2 simplified equations as shown in this equation number 8. This represents simultaneous homogeneous algebraic equations in the unknowns x1 and x2, which represent the amplitude of vibration for masses m1 and m2 respectively. These equations are homogeneous, meaning that they are equal to 0. They are also algebraic because they involve only algebraic terms and not any derivatives. Solving this equation will allow us to determine the relationship between x1 and x2 as well as the natural frequencies of the system. By analyzing these equations, we can gain valuable insights into the mode shapes and natural frequencies of our 2 degree of freedom system. Let's move on to the next step where we will solve these equations to find the natural frequencies. Continuing from our previous discussion, we now need to solve the two homogeneous algebraic equations we derived to find natural frequencies of our system. This involves understanding the concept of trivial and non-trivial solutions. For trivial solutions, x1, x2 equal to 0, there is no solution. For a non-trivial solution, determinant of the coefficient of x1 and x2 must be 0. To find a meaningful or non-trivial solutions, we need to look for conditions where x1 and x2 are not, both are 0. So here we can see this determinant equation, that is, for a non-trivial solution to exist, the determinant of the coefficients x1 and x2 in our equation must be 0, not x1 and x2. This is fundamental principle in linear algebra. Setting the determinant to 0 allows us to find the values of omega, which are the natural frequencies of the system. By expanding this determinant, we arrive this equation 9. This is a quadratic equation in omega squared, which is omega to the power of 4. It involves masses m1, m2, spring stiffness k1, k2, k3, and natural frequency omega. This equation is known as the frequency equation or the characteristics equations. It is a crucial equation because its solutions give us the natural frequencies of the system. These frequencies are the inherent frequencies at which the system will vibrate when disturbed from its equilibrium position. Solving this quadratic equation will give us two values of omega squared, and taking the square root will give us two natural frequencies. These frequencies are fundamental in understanding the vibration behavior of our 2 degree of freedom systems. Let's move on to the next step. Continuing from our previous discussions, we now have the frequencies of our system that we solved. This slide presents the solution to the equation that just we discussed in our previous slide. By applying the quadratic formula to solve the frequency equation, we arrive at these roots represents omega 1 squared and omega 2 squares. These are the roots or the squares of the natural frequency of our system. As you can see, this equation 10 quite complex. It involves masses m1, 2 as well as spring stiffness k1, k2, k3. The equation provides two solutions, one with a plus sign, then another with a minus sign, giving us omega 1 squared and omega 2 squared. These roots omega 1 squared and omega 2 squared are directly related to the natural frequency of our system. By taking the square root of these values, we obtain the natural frequencies omega 1 and omega 2. These frequencies are fundamentally to understanding how our system vibrates naturally. These natural frequencies represents inherent frequencies at which the system will oscillate when disturbed from its equilibrium position. To avoid oscillations and to understand how to avoid, we have to design the systems such a way that the damping will avoid the resonance characteristics. Let's continue. That is, we have now found natural frequencies for our system. But to fully understand the system behavior, we also need to determine the mode shapes that describes the relative amplitude of vibration of the masses at each natural frequency. To find the mode shapes, we need to determine the relationship between x1 and x2, which are the amplitudes of vibration for mass m1 and m2 respectively. We do this by using the equations we derived earlier. By rearranging those equations, we arrive at these ratios. Here, R1 represents the ratio between x2 and x1. R2 represents the ratio between x2 and x1. This ratio depends on the masses, spring stiffness, and natural frequencies. Then, from this equation, we can able to get and express the normal modes of vibrations, which are the mode shapes corresponding to each natural frequency. The normal modes are represented as vectors x vector 1 and x vector 2. As shown in equation 12, x vector 1 represents mode shapes corresponding to W1 squared. X vector 2 represents mode shape corresponding to W2 squared. Each vector contains the amplitude of vibration for masses m1 and m2. Notice how the amplitudes are expressed in terms of the ratios R1 and R2. These mode shapes are crucial for understanding how the system vibrates at each natural frequency. They tell us the relative motion of the masses. For example, if R1 is positive, it means that the masses move in the same direction at the first natural frequency. If R1 is negative, it means they are moving in opposite direction. Hence, this understanding mode shapes is vital for designing the systems that avoid resonance and control vibrations effectively. Now let's look some example to illustrate these mode shapes. We will now look how the motion of the system can be expressed in time as well as initial conditions that influence this motion. Understanding these aspects is crucial for predicting and controlling the system's behavior. We have previously discussed the mode shapes and natural frequencies. Now let's see how the free vibration solution or the motion of the system can be expressed as a function of time. Here we have equation 17, which describe the motion of the system over time for each mode x. Vector 1t represents motion for the first mode. X vector 2t represents motion for the second mode. Notice that the motion is expressed as a cosine function with angular frequencies omega 1 and omega 2 and phase angles pi 1 and pi 2. For the first mode, the motion of mass m1 is given, and as well as the motion of mass m2 is given in this equation 17. Let me see the initial conditions that to fully define the motion of the system, we need to consider these initial conditions. These conditions specify the state of the system at time t equal to 0. Here we have the initial conditions. At time t equal to 0, the displacement of mass m1, which is some constant. Velocity of mass m1 is 0. Similarly, the displacement of mass m2 is rx1 and the velocity of mass m2 is 0. These initial conditions indicate that the system starts from a displaced position with zero velocity. This is a common scenario in any free vibration analysis. By combining these mode shapes, natural frequencies, initial conditions, we can fully describe the free vibration of our 2 degree of freedom systems. This allows us to predict how the system will behave over a period of time. Let's move on to next topic in the next slide. Now, let's put our theoretical knowledge into practice with a concrete example. We will find free vibration response of a 2 degree of freedom system similar to the one we discussed earlier. We are tasked to find the free vibration response of the system shown in this figure. This system consists of two masses M1, M2 connected by springs with stiffness K1, K2, K3. They are given very specific values. These values are K3 equal to 0, K1 equal to 30, K2 equal to 5, M1 equal to 10, M2 is 1. Notice that K3 is 0, which means there is no spring connecting mass M2 to a fixed point on the right. Also, damping coefficient C1, C2, C3 are all 0, indicating an undamped system. This figure shows free body diagram of the masses illustrating the forces acting on them. This already been discussed in our previous slide. Continuing the previous discussion, let we find out the natural frequency for the given specific system. For the given data, the eigenvalue problem will become as, let me recall that we add equation 8 from our general analysis. Now we will substitute the given values for M1, M2, K1, K2, K3 into these equations. Remember that M1 was 10, M2 was 1, K1, K2 values we know. Just we substitute it. As you can see, we replace the values with the numericals. Let by setting the determinant of this coefficient matrix from this equation 1 to 0, we can obtain the frequency equation. To find the natural frequencies, once again I am telling this, the determinant of this coefficient matrix is set to 0. This is the standard procedure in eigenvalue problems. Setting the determinant to 0 gives us the frequency equation. By calculating the determinant and simplifying, we obtain this frequency equation. This equation is a quadratic equation in omega square. It is given by 10 omega power 4 minus 85 omega square plus 150 equal to 0. This frequency equation is crucial because its solutions will give us the natural frequency of our system. By solving this equation, we can determine the value of omega square and then square root to find the natural frequencies of omega 1 and omega 2. These frequencies are fundamental in understanding the free vibration behavior of our system. Let's continue from our previous discussion. We will now look at the results of solving the frequency equation. This will give us the natural frequencies and normal modes of our system. By solving the frequency equation, we find the values of omega square as 2.5 and 6.0. Taking the square root of these values, it will give us the natural frequencies omega 1 and omega 2. Now let's look at the normal modes, also known as eigenvectors. These modes describe relative amplitudes of vibration of the masses at each natural frequency. The equation 4 shows the first normal mode x vector 1. It represents as a vector with components x1 of t and x2 of t. By substituting omega 1 square into this equation we find that the ratio x2 of 1 over x1 of is 2. Therefore, the first normal mode can be represented as the vector multiplied by x1 of 1. Similarly, equation 5 shows the second normal mode x vector 2. It represented as a vector with components x1 of 2, x2 of 2. By substituting omega 2 squared into these equations, we find that the ratio x2 of 2 over x1 of 2 is minus 5. Therefore, the second normal mode can be represented as the vector 1, minus 5 multiplied by x1 of 2. This normal mode tells us how the masses vibrate relative to each other at each natural frequency. In the first mode, masses move in the same direction, with the amplitude of mass m2 being twice that of mass m1. The second mode, the masses move in opposite direction, with the amplitude of mass m2 being 5 times that of mass m1. Understanding these natural frequencies and mode shapes is crucial for predicting and controlling the vibration behavior of our system. Let's move on to discuss the results. From the previous slides, let's use the given initial conditions to determine the specific values of the constant x1 of 2, x1 of 1 and 2 and psi 1 and psi 2 in the free vibration response equations. These equations represent free vibration response of the mass m1 and m2 respectively. By substituting the initial conditions into these equations, we can solve for the unknown constants. Equation 8 through equation 11 shows the initial conditions for the displacements and velocities of the masses at time t equal to 0. We will use these equations to solve for the constants. To solve these equations, we can start by substituting t equal to 0 into equation 8 and 1. This gives us two equations into two unknowns. We can then solve this equation simultaneously to find the values of x1 of 1, x2 of 1. By following these steps, we can determine the specific values, that is displacement x1, x2 as well as phase difference phi1 and phi2. These values will fully define free vibration response of the 2 degree of freedom systems. I have to remember some important points here, emphasizing that the initial conditions are very important to determine specific response of the system. Similarly, free vibration response is a superposition of two harmonic motions, each with its own natural frequency and amplitude. Third, the physical interpretation of x1, x2, pi1, pi2. That is, for example, x1 and x2 represent initial amplitude, means pi1 and pi2 represent initial phases of the vibrations. Continuing our analysis from the previous slide, we will now solve these equations we derived using initial conditions. This will give us the specific values of the constants in our free vibration response equations. Let we take the equation number 8 and 9. These equations involve initial displacement of the masses. Solving this equation 8 and 9 simultaneously giving us the values x1 cos pi 1 and x1 cos pi 2. As shown in equation 12 equals 5 by 7 and similarly x1 of t equals 2 bar 7. The solution equation 10 and 11 leads to this. Now, this equation involves the initial velocities of the masses. Solving these equations simultaneously giving us the values of x1 of 1 sin pi 1 and x1 of 2 pi 2. As shown in equation 13, Sine pi 1 is equal to 0 as well as sine pi 2. Now let's combine the results from the equations to find the values of x1 of 1, x1 of 2, pi 1, pi 2. So as shown in this, x1 equals 5 bar 7, x1 of 2 equals 2 bar 7, pi 1 is 0 and pi 2 equals 0. These are the specific values of the constants in our free vibration response equations. These values complete our solution for the free vibration response of the system. By substituting these values back into equations 6 and 7, we can fully describe the motion of the masses over a period of time. This allows us to predict how the system will behave when subjected to the given initial conditions. We have now determined the specific values of the constants in our free vibration response equations. Let's see the final form of this equation, which describes the motion of our masses m1 and m2. By substituting the values x1 of 1, x1 of 2, pi 1, pi 2 we found earlier in the equation 6 and 7, we obtain the final free vibration response equations for the masses m1 and 2. So, we derived the equations describing the free vibration response of our given 2 degree of freedom system. But what does this actually in terms of physical motion of the masses? Looking at these equations and the visualization, we can see that mass oscillates with a combination of two frequencies omega 1, omega 2, where omega 1 is 1.5811 radians per second, omega 2 is 2.4495 radians per second. These are the natural frequencies we calculated earlier. This amplitude and phases of these oscillations are different for each mass as determined by the constants we solved for. For example, mass m1 has a larger amplitude for the oscillation at omega 1 compared to omega 2, while for mass m2 it's the opposite. Also, the oscillation for m2 at omega 2 have a negative sign indicating a phase difference compared to m1. Hi. Let's we complete the basic derivation of natural frequency and mode shapes for the two-dimensional systems, that is 2 degree of freedom systems. Let's move on to few more problems. Let me solve all those problems to see how to find natural frequencies for the given systems. Let I see you in next video. Thank you.